Okay, so steps to solving a work energy theorem question. Obviously, always write out your givens. Okay, if you've identified it as a work energy theorem question, write that work is a change in energy. Okay, it may be that force times distance is a change in energy. Okay, then identify the type of energy being changed. Is it potential or is it kinetic? Okay, these things here, okay, will be up here once you've decided that. Okay, so the change in energy could be a change in potential or a change in kinetic. Okay, then you're going to set up work energy theorem. Okay, so you could have work is EF minus EI or FD equals EF minus EI. Okay, and that could be for kinetic or potential. Incidentally, when you get to physics 20, you'll get questions where both change. Okay, it actually isn't any harder. You just have a few more things to keep track of. Okay. And then lastly, manipulate and solve. Okay, so manipulate for whatever you were supposed to solve for. If it was VF, manipulate for VF. And so, okay. I want you guys to try this one here. So I have a person who uses an unknown force to lift a 50 kilogram mass to a height of 1.5 meters. Okay, we're looking for how much force was used to do that. Okay, the answer is there, 490.5 newtons. It should probably only have two significant figures though, so it should probably look like this instead. Okay, so give that one a try. What kind of, sorry, let's write down our givens first. All right, so we have a height of 1.5 meters. Now, it just so happens that if I'm lifting something, the height and the distance over which I'm exerting the force are the same number. So this number is actually going to be used twice, okay? Two different places. The mass was 50 kilograms, okay? And obviously G is 9.81. How do I know I need to use G here? What kind of energy is changing? Potential, right, gravitational potential energy. So that was my next step. Work is a change in gravitational potential energy. Oops, still got all my work down here. Okay, so that's going to mean force times distance equals m times g times h final minus m times g times h initial. But since it says it's lifted to a height of 1.5 meters, where do we assume it was lifted from? From the ground, so there was no initial potential energy. Now, here's the thing, guys. Force times distance equals potential energy final. It actually equals force times distance. If you look on your formula sheet, the force of gravity is calculated by multiplying mass times gravity. And a height is a vertical distance. So really, we're saying force times distance equals force of gravity times distance. That should make sense. Force times distance equals force times distance. Those two things should be equal. All right? Okay, so if we're manipulating here to find the force that was used, we're just going to divide both sides by d. Okay? We can make our life really easy because we can recognize that height and distance are the same number, so they'll what? Okay? To lift something, I only have to lift as heavy as gravity pulls. Lift as hard as gravity pulls. Lift as heavy, whichever. Okay, does everyone kind of follow me there? Right, so I have to work against the weight of the object. Right, so if I want to lift it, I just have to exert the same amount of force that gravity pulls down with, and I'll be able to lift it at a constant velocity. So all I had to do is go m times g, which is 50 times 9.81, 9.81, and that's going to equal 490.5. But again, we only have two significant figures. 4.9 times 10 to the 2 newtons. Guys, a really common mistake is to get the wrong units on things in work energy theorem. Okay, I see people confuse newtons for joules and vice versa all the time. Okay, remember, energy and work are in joules. Force is in newtons. Okay, so they are different things. All right, any questions on what we did there? Okay. You like my diagram? I think it's terrible. And it's in pieces, apparently, too. Okay, so the answer to this one, spoiler alert, is 10, actually not 10.9 meters, 11 meters. Because it's got to have the right number of significant figures. All right, so we have a heavy box, 35 kilograms, pushed up a hill by a force of 150 newtons over a distance of 25 meters. How much higher is the box at the top of the hill? Okay, and we talked about this when we had that picture of the person lifting the square block and the person pushing the block up the ramp. Okay, what kind of energy are you changing if you push something up a ramp at a constant speed? No, I'm pushing it at a constant speed. I'm not changing its kinetic, it's potential, right? If I push something uphill, I'm changing how far above the ground it is, agreed? Or how far above the bottom of the hill, at least, it is. All right, so I'm changing the potential energy. Okay, so our givens are that we know the mass is 35 kilograms, okay? We know the force being used is 150 newtons, okay? And we know the distance over which it's exerted is 25 meters. Now, that 25 meters is not the height at the top of the ramp. It's the what? It's the length of the ramp. Okay? When you push something up a ramp, you have to push it further than you would have to lift it if you lifted it directly to the top. Okay? That's what we talked about the other day. So this is our situation. Okay? We have a 25-meter long ramp with a box on it that's being pushed with 150 newtons worth of force up the ramp. Okay? When I do this, what I'm actually doing is I'm changing the gravitational potential energy from the bottom of the ramp to the top of the ramp. Because I'm pushing it at a constant speed, I don't change its kinetic energy at all. Okay? It's just moving at like 1 meter per second or whatever. Okay? Its kinetic energy isn't changing in this case. Okay? So it ends up here at the top of the ramp. It started down here. So what I need to do is find out how high is the ramp. Right? If I had another side, I could use trigonometry, but I don't. So I'm going to have to use work energy theorem instead. Okay? So I'm going to say that the work being done in pushing this thing up the ramp is equal to the change in the potential energy. So that's going to mean the pushing force multiplied by the length of the ramp equals m times g times h final minus m times g times h initial, which is 0. All right, so now all I have to do is solve for height. Okay, so I just divide both sides by mg, okay, and that'll give me my final height. All right, so I've got 150 newtons times 25 meters divided by
35.
Sorry, no, 35 is the mass.
Yeah,
Thank you
no,
very
he's
much.
right. Well, you're wrong, he's right.
35 times 9.81. I realize I haven't got a lot of sleep. I realize I'm old. But I'm right. I realize I'm right. I'm not taking it personally yet. All right, 150 times 25, okay, divided by 35 times 9.81. Okay, so we got 11 meters as the height of the ramp. Okay, everybody all right with that? Are we starting to see the pattern here?
Final.
Yeah. Yeah, I mean, that's the thing. You have to do a few until you see the pattern, but the pattern's always the same. Okay? We figure out what kind of energy is changing. We set up a work energy theorem. We solve for what we're looking for. Okay? All right. I think we got time to at least try this one. Okay? So we got a pitcher that throws a ball. The mass of the ball is 0.250 kilograms. They exert 300 newtons worth of force on the ball over a 2.2 meter path. We're looking for the speed they will release the ball, okay, or the thrown speed of the ball. Right? What can we assume the initial speed of the ball is? 0. Okay. All right, give you a little bit of time to work on that. We're going to leave here for mass in 3 minutes.